All right, guys, so we're going to look at a couple of these little mechanical equilibriums, simplify something down to figure out a net force, or if you're given a net force, what the other forces would have to be. So in the first problem, when they said the net force was going to be, it has to be 3 newtons to the right. This was blank and this was blank. So if they say 3 newtons to the right, what that means, the top and bottom have to balance no matter what, because the net force is to the right. So automatically put a 12 there. I put this little equal looking sign there. Boom, I know that they're good. If the net force is 3 newtons to the right, that means this rightward force needed to be 3 greater than the left. So 3 greater than 12 is 15. Boom. Next one, F net, 40 to the left. It means top and bottom have to balance, so the bottom is 45. And if it's 40 newtons to the left, that means this left force has to be 40 greater than the right. So 60 minus 40 would give me 20. 15 newtons up. Since they're saying up or down, that means left and right have to balance. So we got 80 to the left, and F net is 15 newtons up. The upward force has to be 15 greater than the bottom, all right, or the one going down. So 75 minus 15 is 60. Net force of 0. Top and bottom have to balance, and so does the left and right. And boom, done. Now this one had 2 blanks here, but you can't let them be zeros because there is an actual vector, so you have to have a number. Basically anything greater than 1, but they would have to be the same. So I just picked 100 for each. So what really mattered was they said the net force is 8 newtons to the right. I had some people in my one class put 108 over here because they just saw 8. But again, direction matters. So if the net force is 8 newtons to the right, that means the right force needs to be 8 bigger than the left. So 100 minus 8 will give you 92. Okay, so now what you guys are going to be doing is, can you pass these out for them? All right, so our little free body diagram, all right, assignment here. Essentially, this is the same kind of scenario. All right, this would be the same kind of scenario. Oops, I apologize. That's not the one I want to do first. This is the one I want to do first. Silly me. Yep. So the one that we're going to take a look at first is this one, because it kind of summarizes what we dealt with yesterday. So guys, what is a vector quantity? So have your notes out and just start kind of shouting them out with me. So what do we got? What is a vector quantity? Who knows? What does a vector quantity have? Good. It has magnitude, unit, and a direction. So displacement is one of those, is a vector quantity. Velocity is one of them. Acceleration is one of them. So are forces. Okay, what unit do we use for force where the symbol is capital N? Newtons. All right, it's the Newton, or newtons, capital N. What does the term net force mean? It means the sum of all the forces. So we add everything up, left and rights, or if they're in the same direction, we add them, opposite directions, we subtract them. Mathematical symbol. So this right here means the sum of the forces. Sigma in math terms and statistics means the sum of, right? We have added a bunch of whatever together. The sum of, capital F, sum of all the forces is equal to 0 newtons, and or the symbol for net force, we would say, is F net, technically, right? F net is equal to 0 would mean there's 0 net force. If the sum of the forces is 10, okay, but we would then use more so net force, F subscript net. Okay, we had that right from our notes. Okay, right now we need to draw and label the net force. How many forces are acting on this thing? 3. So can the object have ever, if there's only one force acting on it, can it have a net force of 0? No, right? Because I'm not subtracting anything. So yeah, it can't be. And then what happens if you do not have a net force of 0? Something's going to happen. Your motion is going to change. If F net is greater than 0, your motion is going to change. So we would just say, okay, 3 newtons to the left. That is our net force. All right, if we don't remember, same direction, what do we do with them? Add. Opposite directions. Subtract. Okay, what about this next one, guys? What would the net force on this one be? You have 8 to the right and 3 to the left. What's 8 minus 5? Sorry, 8 minus 3. That is 5. So the net force for this one, guys, is going to be 5. But what direction? Good. To the right, because 8 is greater than 3. So basically, if you were playing like tug of war, all right, me and Chris is pulling with 3, I'm pulling with 8, I would move, all right, the rope right in my direction. But I'm not moving it over with a full force of 8 because he's pulling against it. So we'd only be basically pulling with 5 newtons, and it would be going to the right. So that's my net force. The net force up here, I'm just recording it. That's right. Yep. So the net force here, correct. So you have 3 to the left and 5 to the left. Since they're in the same direction, we add them. So basically, we would have 8 to the left. If you have 8 to the right, what happens then? Opposite direction, we would subtract. So 8 minus 8 is 0. Now, if there is a net force of 0, we don't even need to draw in a net force vector box here. It's just going to be F net is equal to 0. Okay, darn, what goes on now? So what this is saying here, what happens, all right, so that should be pretty simplistical, guys, for summarizing it and nailing it down to just one net force. But what happens if you have a net force in the x and y direction instead of just one? What do I mean by that? Okay, so we're going to need this equation. C is equal to a squared plus b squared square root. So in this first box, I'd like you to just figure out right now, what is the net force in the y directions? So what does that mean? Y direction is what? Up or down or left or right? So y and x, right? So what is the net force in the y direction? If I cover up the left and right, what is the net force right here? If you have 5 up and 4 down. What? I just didn't hear you. What's that? Not 9. 1, because they're going opposite directions, so we're going to subtract them. So it would be 1 going in what direction? Up or down? Up, because 5 is bigger than the 4. Okay, so on this one, we're going to just draw a little arrow going here, up. So that's 1 Newton. And now we're going to take a look at the x direction. What would my net force for this one be? If I have 7 to the, all right, good. And in what direction? Good. So on this, we're going to draw this over here. We're going to draw. It's going to be a little. It's got to be bigger than the 1, but not like, don't go crazy. Okay. So I'm going to zoom in a little bit here now. All right, now I don't know what to do. Mr. Lombardo, what in the heck do I do now? All right, well, from the notes yesterday, guys, we had said that you can kind of take your vectors and you can kind of move them around a little bit without changing their values. So what does that mean? I basically could go like this. I could take this dude and I could put it here. Because remember, you're still essentially like you're moving up and to the left. So your overall would be somewhere in this direction. Now if I just grab this dude here, moved him over, head to tail method, what you would be asked to solve for is basically this green. So that's what we're going to do with the equation. All right. So what direction would your net force be in? If you say up is north, right is east, down is south, and west is left. You're going in what two directions? North and west. So we're going to be somewhere, our net force is going to be somewhere to the south, to the northwest. So a slant like in this direction, but it would be closer towards the 4 because that's the bigger number. So it's going to be somewhere in this direction. Now we got to figure out what that number is. And we do so by using this equation. 1 and 4 are going to be your A and B. Does it matter who's who? No. So if I did 1 squared plus 4 squared and I took the square root of that it would be 1 squared is 1, 4 squared is 16, so it's the square root of 17. And that comes out to give us approximately 4.12. So our final answer to this thing would be 4.12 newtons. And if we had to give a direction, right, we draw it this direction. And if there wasn't, we could say northwest. And that would be your full, complete answer and how you get to it. Boom. Okay. Now, this, guys, is just for the conceptual parts, right? Like, so it's talking about our states of equilibrium. What does the word equilibrium mean? What's the first part of that word? Equal. So if things are equal, it means basically, yeah, a lot of stuff has to be equal out, or in this case, balanced out, in order for it to be in a state of equilibrium. So to be in a state of equilibrium, you have to have a net force of 0. If the net force of an object is 0, what's going to happen to the state of the motion? Okay, so from the notes, no change in motion. All right, or it remains the same. If it's not 0, what happens? The motion changes. And how does motion change, guys? Basically, right? We basically said, right, if an object is going to accelerate, it can accelerate in 3 ways. What were those 3 ways? Think about it on a car. Gas to speed up, brake to slow down, and steering wheel to change direction. So to change direction, you have to have a net force greater than 0. To speed up, you have to have a net force greater than 0. To slow down, you have to have a net force greater than 0. But if you don't want to change what you're doing, okay, you have to have a net force of 0. So when an object is in a state of mechanical equilibrium, what does that mean about the net force? That would mean that the F net is equal to what? 0. What else does that mean? What else does that mean? It means what is happening to the object's state of motion. If F net is 0, no change in motion. Write a single equation that represents an object in a state of mechanical equilibrium? Sigma F equal to 0. All right, the object is is in a state of equilibrium. Okay, now what do we have? There are two types of equilibrium. From your notes, guys, what were those two types? Static equilibrium and, yep. What does static mean? Object is at rest. So not a good at. So. Okay, gosh, that's bothering me. At rest. Okay, so remember, mechanical equilibrium. What does that mean? F net has to equal 0. So that means you could be in static equilibrium, or you could be in dynamic equilibrium. What does dynamic equilibrium mean? It means you have to be at a constant, not vector, but velocity. Velocity is what, essentially? Speed with a direction. So if you're at a constant velocity, you have to be at a constant speed in a straight line. If you, turn at all, you can't be in equilibrium if you speed up or slow down. So guys, let me ask you this. Is there a way you can be moving at a constant speed and not be moving in dynamic equilibrium? How? If you're moving in a circle, right? Because you would be constantly changing direction, which means you would be changing your velocity, and you wouldn't be in equilibrium. So basically, like being in a car on a straight line road, okay, on cruise control. You're not speeding up, slow down, you're staying straight. But if you're on a racetrack, a perfectly circular racetrack, and you put cruise control on, and you're moving around in a circle, well, you're constantly changing direction, so therefore you would not be in equilibrium. Okay, look at this object. What is my net force going up? 2 plus 3, same direction we add. So we got 5 going up. 6 plus 6, what is that? So I'd have 12 to the left. How much do I have going down? So 5 up and 5 down, they balance. 7 plus 5 is how much? 12. So you have 12 left and 12 right. Those guys would balance. So they ask you then, is this thing in a state of equilibrium? And how do you know it? Yes, because the sum of the forces equaled 0. All right, we added forces in the same direction, we subtracted in the opposite direction. Can you conclude, based on the information, whether this is static or dynamic? Explain why or why not. Well, all I know is that, what? The net force is equal to what? 0. So if the net force is equal to 0, what could it be in? Static or dynamic? So do you have enough information to tell you which one it is? No. So no, not enough information. We just know that the net force is 0. And then the last one. So what can you conclude about the object's state of motion? And what can't you conclude? Well, if the net force is 0, what happens to the object's motion? Good, it does not change. So we know that the motion is not changing. And then what can't you tell? Close. Can't say if it's in static or dynamic. Equilibrium. Okay. So then the other thing that I want to run through with you guys. All right. The front side of this we did, all right, basically on the homework together. So you don't need to worry about this one or number 2 right now because those ones are pretty easy. There's no pass. Up top. Blue. Just make sure it comes back, not folded. Okay, now, so you guys should be good with this. All right, it's going to basically tell you, determine what the net force is on these. So you break it down to net force. Number 2, you had to determine what each value had to be in order to make the net force true, which was basically what you guys did for homework, and we had an example like that in our notes. So what we're going to do right now is we are going to complete, all right, what is a free body diagram? A free body diagram, guys, is pretty much a box that we draw that we show all forces on an object, because that can help us determine, all right, what things are important and what aren't. Because sometimes you read a word problem, it can be a lot of information, but some of it may not actually be needed. So plus, visually it helps sometimes figure a couple different things out. So anytime you see the word at rest, what does the F net got to be? Good. All right, and that means everything has to balance. And the same thing, if you see constant velocity, F net is equal to 0 newtons, which also means everything has to balance. So a free body diagram of a book at rest on a tabletop. So because it's on a tabletop, I'm just drawing a flat line like this, and I'm just putting a box here, a little square. The square can represent anything. It could represent a horse and a carriage. It could represent a sled, a box, a fridge, a baby seal, whatever. This is at rest. So yesterday we mentioned one of the forces. Anything that has mass and is under the influence of gravity has F sub g, which is your force of gravity on the object. Or what we will also call the weight of the object. And if you needed to solve for the equation, right, if you actually needed to solve for the value, if you know the object's mass and we use gravity, mass times gravity will give you that. And then what force, again, this thing has to balance because it's at rest. So that means you have to have a force going opposite direction, equal in size. So these two things have to be equal. And that force was what we called the normal force, F subscript capital N. Okay, and for that to work, or to have the normal force, you need to be against a surface. You need to be against a surface. Okay, so we're done with that one. When an object is in free fall, if an object is in free fall, only under the influence of gravity. All right. Thank you, bud. You too. Just gravity. All right, or the only force is gravity. Which is why they say right here, all right, neglect air resistance. So there's no other force. So now I'm not on a surface, so I'm just going to draw my box. Okay, this box is an egg. And it has mass, so if it's free falling, the only thing that's going to be acting on it is Fg. And if it's free falling like that, and the only thing that's acting on it is gravity, it's going to be accelerating downward. Flying squirrel is gliding with no wing flaps from a tree to the ground at a constant velocity. What do we say about constant velocity? Constant velocity means F net is equal to 0, which means everything has to balance. Okay, so again, we're flying through the air. So you have your object. This time, this box is a flying squirrel. What force are you always going to draw, guys? Fg. In what direction? Straight down. If this thing is saying it's constant velocity, right, F net has to be equal to 0. We need a force that goes up and is the same size. Okay, so normally if we're on the ground, you would have normal force. But in this case, we're supposed to be considering air resistance. So we would have F subscript air. And that's your air resistance. And these two guys would need to be equal. So here you go. You're good. It's not too bad. Okay, now we're looking at number 6. Whoop, don't want that. All right, so we have a rightward force that is applied to a book or in order to move it across the table with a rightward acceleration. So there's a couple things we need to know. Okay, F applied, all right, is your applied force. And that can be a push, a pull, a kick, a tackle, something, right, etc. So F applied is a push, pull, kick, whatever. Okay, now when they say the words here, rightward acceleration. Okay, so if that's the case, we have a rightward acceleration. Acceleration is always in the direction of the net force. All right, and now since it's moving, they said moving to the right. We know that means, all right. If the acceleration is to the right, that means the net force has to be going to the right, which means the rightward force needs to be greater than the left. All right, so F net needs to be greater than 0 and to the right. Okay, so we have a book across the table. First thing, what force should you guys always draw on first again? FG, and what direction? Straight down. Is it on a surface? Yeah, it's on across a tabletop. So if it's across the surface, what force goes against gravity? Fn, or your normal force. And guess what? Is the book moving up or down? No, which means those two have to be equal. Okay, so that takes care of one of them. Now, it says consider friction forces. Okay. A rightward force is applied to a book. So that, right, a rightward force is applied. So that means our applied force would be going to the right. Now, guys, remember it says it's accelerating to the right. Acceleration is in the direction of net, all right, the net force, which means the right force, all right, our vector to the right needs to be bigger than the one to the left. So we're going to have, okay, applied force going to the right. And it says consider friction forces. Friction, we're going to make it a little bit smaller. That's F lowercase f. All right, and friction goes opposite the direction of motion. So if this thing is moving to the right, friction would be going to the left. It has to be. And now, since the applied force is greater than the friction force, right, if we wound up redrawing this to just show the single net force on it, it would have to look like this. If the top and bottom balance out, applied force minus friction force would still give us a force to the right. It would be smaller, but yeah, that would be your net force. No. Constant velocity, what does that mean, guys? F net has to be what? F net needs to be equal to 0. So very similar to the problem above, except what does it say? It says, okay, we got an applied force going to the right, but the thing is moving at a constant velocity. Consider friction forces. So guys, if something's moving at a constant velocity, what does that mean about the forces? They all have to balance. So you would have the same thing. We always draw an FG. It's not moving up or down, so the top and bottom have to balance. So your normal force and gravity, all right, your weight of the object, balance. Applied force is going to the right. All right, so it could be our push, right? And if what the applied force stands for is force, which is a push or pull, basically. So we have a push or pull force here. That's our applied force. It's moving to the right, but it's moving at a constant velocity, which means the friction force has to be equal to that. And everybody is balanced and everybody is equal. Number 8 is just kind of like the squirrel. All right, so number 8 is like the squirrel problem. And number 9 is going to look pretty much just like number 6 at the top. So the only one that's left that's going to be slightly different is number 10. Okay, what's going on here? A car is coasting to the right. Guys, you know what that means? When a car is coasting, what does that usually mean? Not necessarily drifting, but if you're driving and then basically take your foot off the gas, you're just coasting. Now you're letting the car just kind of basically do its thing. What is it doing? It's coasting to the right, but it's also slowing down. So that slowing down is a big piece of information. All right, so we're coasting to the right. So this thing is moving to the right. but it's slowing down. So I'm going to write this off on the side because this is the interpretation of that. Okay, we are still moving to the right. Now, if you take your foot off the gas, what is the car going to do? It's going to slow down. Why do you think it's going to slow down? Because of what between the tires and the road? Good. So while friction is slowing it down. What direction does friction go? I think we wrote it at the top. Oop, I cannot spell. It always goes opposite the direction of motion. So if this thing is moving to the right, friction acts in the opposite direction. So even though this thing's moving to the right, what direction would friction then have to be? Opposite. So if it's moving to the right, friction would have to be going to the left. Okay. So we have a car on a road. Car on a road. What vector do we always draw in? FG, our weight. It's not moving up or down. So, and it's on a surface, so normal force, gravitational force, okay, balanced. And I will just say, normal force is it's always perpendicular to the surface, but we're not doing any problems on an angled surface. But if it was, all right, the normal force would be going up, and as this whole thing changes, the normal force makes it still 90 degrees, but we don't have to worry about that. All right, thing is moving to the right, but does it say like you're coasting? So you're not hitting the gas anymore. So you have no applied force. So basically you're moving to, this whole thing is moving to the right, but it now stops. I'm sorry, there's no longer a force acting on it. So you take your foot off the gas, there's no more applied force to the right. The only other force acting on it would be friction. And if it's moving to the right, friction has to be going in the opposite direction. So friction would be going to the left. So the top and bottom balance out, and friction is in this direction. So if I had to simplify that, right, and just draw one net force, FF, going to the left, okay, it means it's basically slowing the object down going to the left. But like this whole thing is still moving to the right because friction goes opposite the direction of motion. All right, so you guys can finish problems 8 and 9. All right, 8 is just like the squirrel problem on the page we did before this, and then number 9 is just like the one number 6 at the very top that we just did. Okay, so 9 is very much just like number 6. And then you guys will complete these dudes. You're pretty much just finding what the net force is. And then the last thing you are doing is you are going to find what each letter has to be in order for the net force to be true. Okay, like you did on your homework, and we did a problem very, very similar to this also in the notes yesterday. All right, so guys, that will be your homework, and that's going to be due Friday because I don't see you guys. Okay, all right.